This is Y490 Politics of the Internet. This lecture was originally delivered on January 11, 2012. This course deals with the history of a particular technology, and so I thought I'd start a little bit with a more general introduction to technology and the history of technology. First of all, there are different ways of thinking about technology. First of all, as tools, then as knowledge connected with the use of tools, as ways of organizing human activity. For example, Ford's invention of the mass production techniques that created the Ford Model T, and ways of creating and embedding new knowledge in products and processes. The last is a somewhat more modern one, connected with computers and hardware and software. Sort of from left to right, the images here represent the evolution of tools from the simplest tools such as axes and hammers made out of stone lashed to wood, to metal hammers, the sword in the second picture, of electric drills in the third picture, and computers on the fourth picture. Some tools are more general than others. That is, they can be used for different purposes, and some tools allow themselves to be programmed, which means that they're general tools but can be programmed to do more specific tasks. When we talk about making things, a distinction is made between mass production technology and craft technology. Craft technology generally is something that requires quite a lot of skill on the part of the user, and there's no guarantee that different users will produce exactly the same product. That we often highly value that, for example, in the making of ceramic pottery, or for that matter, any kind of artwork. And that kind of production is often called craft production, until the invention of mass production technology, which requires certain kinds of machines and measurement technologies. Then all production was really craft production. When all production was craft production, individual workers had to possess special production skills. When mass production was invented, workers with relatively lower skill levels could be used to make things. A great example of this is in Charlie Chaplin's portrayal of a worker in Modern Times. I see a picture up there on the upper right-hand corner. I do recommend that you look at that movie for a comedic spoof of that change to factory work. Highly skilled workers were still needed to make and program general purpose machines, and to, for example, create machine tools and use machine tools to produce custom parts for factories. Ways of organizing human activity have played a very important role in modern technology, not just in the creation of factories and mass production techniques, but also in the invention of new forms of organizations such as the multinational corporation. Even back in the days of primarily craft production, we had ways of organizing human activities such as the creation of guilds of skilled craftsmen that played a very important role in the way technology evolved. And now we also have quite a lot of innovation in the way products are sold, so Walmart being a great example of that. And to some degree, you can think of organized unions as being a form of human organization that help to transform production systems. Many modern technologies contain embedded knowledge. That is, the product, the object itself, uses various ways to store information which is useful to the user or customer. So, for example, operating systems in computers, such as the Windows operating system in PCs, or the operating system that are contained in Apple PCs, is a way of embedding knowledge into the product. Software is now a common way of embedding technological knowledge into tools, processes, and end products. Many modern technologies, unlike older technologies, are not the result of trial and error discovery methods, but rather of more systematic methods that generally fall under the rubric of science. Many areas of science are not connected with technology per se, but many are. There is a lag between scientific discovery and the application of that discovery, sometimes as long as 10 to 20 years. Depends on the regulations involved in introducing new products to market. But that lag is getting shorter and shorter as we get better and better at applying science and technology to the creation of new products. Ed Mansfield, an economist, was very interested in this phenomenon, so that you can see in the chart in the lower left there his work on how knowledge had to occur before the implementation of that knowledge, and that the gap could change over time. He particularly argued in the upper right-hand thing that knowledge had to be, people had to be persuaded to apply knowledge to a new product or process. They had to decide to do that. Then they had to implement it, and finally they had to figure out a way to actually make it work. Some innovations diffuse more rapidly than others. A great example of a rapidly diffusing technology is television. Somewhat slower was the diffusion of electricity. Here's an example or a graph that shows that if you start with 0 being the date of introduction of the new technology, you can see that cell phones actually are the most rapid in being taken up, followed by PCs, VCRs, and televisions. Somewhat slower are automobiles and electricity. The telephone itself, since it was introduced in 1876, obviously took a long time to become a nearly ubiquitous feature of most homes. Patents and copyrights and other forms of intellectual property protection were invented in order to create a monetary incentive for innovation in new technologies. In exchange for inventing a new product or process, the owner of a patent is given a temporary monopoly. In the United States, we have a very important legacy, mainly from World War II, in the form of Vannevar Bush, who really was the father of the National Science Foundation and invented many of the concepts that we now currently apply to this issue, the issue of science and technology. He distinguished between basic and applied research. He argued that the government should help to fund basic research, but probably not applied research. And he argued that there should be peer review of proposals for research projects submitted to the government. We have had a number of very large research and development projects funded by the U.S. government. Ones that are most visible are NASA and the space program, started under the Kennedy administration. We have the cancer research, which started under the Nixon administration, and the Defense Advanced Research Projects Agency, which was created in the 1950s by the Eisenhower administration, but has played a key role, for example, in the invention of the Internet. So here's a picture of Vannevar Bush. He lived from 1890 to 1974. He was a very early computer scientist, actually before there were computers, at least digital computers. And he helped to establish the National Advisory Committee for Aeronautics in 1939. He became head of the National Defense Research Council in 1940. And he did not actually become the director of the National Science Foundation, but he was a key person in persuading the government to adopt legislation that created the NSO. This just reviews earlier comments I made about Vannevar Bush's idea that basic research rather than applied research should be the focus of government-funded research. He thought that private industry should work on applied research. That's converting basic knowledge into applications and actual products. He also thought that university research should be funded based on competitions where grant proposals would be peer-reviewed. Here's some examples of basic versus applied research. So a basic question is driven by the curiosity of scientists. How did the universe begin? What are the origins of life? And applied research is usually designed to solve specific problems or particular problems. So how can we improve the yields of specific crops, such as corn or wheat? How can we make our digital televisions work better? That would be another example of applied research. The National Science Foundation was founded in 1950. Its annual budget, roughly $6-7 billion a year, accounts for about 20% of all U.S. basic research conducted by universities. The funding priorities are based on views of the scientific community. The space program was actually NASA, the National Aeronautics and Space Administration, was created in 1958. Got a big boost during the Kennedy administration with the idea of putting a man on the moon. The NASA budget of a few years ago was around $15 billion. It's gone down since then. There's been a recent scaling back of manned space flights, so that actually some private commercial companies are moving into that area. But there's a picture of the space shuttle and a view of the Earth from outside. Private contractors have already been important players in the space program. Recently, starting with the Reagan administration, there's been an effort to privatize part of the space research effort. There are private spaceflight companies that have expanded recently to service possible future markets for space tourism. An example is Spaceship One, which has been designed by Vern Rutan and sponsored by Richard Branson, the businessman who's behind Virgin Records. He actually created a subsidiary called Virgin Galactic to continue working in this area. So I think I'm going to skip over this slide. Here's a National Institute of Health budgets for roughly 20 years. You can see that National Institute for Health budget is even larger than the NASA budget and considerably larger than the National Science Foundation budget. Defense research and development spending is also fairly important. Most Defense Department spending is devoted to military use technologies, although some dual-use technology research goes on under the auspices of the Defense Department. This became a political issue in 1994 when the Democrats lost control of the House in the 1994 elections, and so a lot of that dual-use technology support was cut after 1994. Hasn't quite recovered. Government funding of R&D and information technology has been fairly robust. You can see that defense leads all the other categories. Non-defense has kept up pretty well, though, and that space and general science research for computing and information technology has not been insubstantial. Generally speaking, the industry research spending has exceeded government spending for quite a long time, although, as I said before, most industry research is applied research, not basic research. The Defense Advanced Research Projects Agency is one of the important agencies within the Defense Department that funds research in science and technology. It was begun in 1958, partly as a reaction to the launching of Sputnik by the Soviet Union. And initially it focused on the race to space. In the 1960s, a new office called the Information Processing Techniques Office was created under the leadership of J.C.R. Licklider. Licklider was very important in pushing for time-sharing computing research and also helped to create the program which eventually resulted in the Internet. So the particular research was at Bolt, Beranek, and Newman, which was sort of a private public think tank in Cambridge, Massachusetts. There, Vint Cerf and Robert Kahn helped to develop the set of protocols that became the basis for the Internet. So DARPA has been successful in a number of areas in what eventually became the Global Positioning System, or GPS. It was very important in improving the accuracy of intercontinental ballistic missiles, helped to create the internet, smart bombs, and other types of smart munitions, and also funded some display technologies that eventually were successful, such as digital light processors and that type of television display. So let's turn now to what the internet actually is, and the sort of simplest and most technological definition is that it's a network of networks, that it allows networks to connect to one another, and that the main underlying technologies are that you have digital data moving from one machine to another. You use a kind of way of moving that digital data, which is called packet switching, and that all of this falls under rules or protocols called the TCP/IP family of protocols. The idea initially was that this should be a global system with no boundaries between geographically separate political areas, and therefore potentially global in scope. I want to end with this slide, which is sort of slightly different from the question of what the internet is, and that is a kind of related concept which has been popularized by certain science fiction authors, particularly William Gibson, whose picture is on the right there, with his first major book called Neuromancer. In any case, people argue that cyberspace is a kind of new kind of space, a virtual space rather than an actual space, and that it is a little bit more than simply the technologies behind the internet, but rather a kind of way of experiencing the world. We can see that with the addition of social networks and social media, there actually is the creation of what you might call virtual communities, which link people across time and across space in ways that were never possible before, and obviously much less expensive than previous technologies. So we'll talk more about that later.